So this is an in-class quiz.
Yes. Yes. Exactly. I mean, ideally, all of them had to be in class, but because we have already a short time for our lectures, I did not want to have most of the other ones. I give them to you after class, but this one is in class. Okay. Now, what we are going to do today and what we are going to do next week. As you can imagine, we've talked about amplifiers quite a bit, but at the same time, I understand it's kind of confusing. I mean, I think it should have been confusing for everybody because there are so many concepts that we throw right one after the other. And so what I decided to do is to cover the material, but then all of next week, we are going to do examples on amplifier design, including low noise, maximum gain. We'll look at stability. We'll combine now. So next week, we are going to solve problems. And we are going to combine all of these concepts because after this project ends, which is on filters, then the next one is going to be to design your low noise amplifier. And so I want you to be well ready, to be able to do that, because after that, you will have to combine everything and then try to write your project for the class with detailed designs for a few things, not for everything, obviously, in your receiver. So that's what we are going to do. And after that, we are not going to do oscillators, but we are going to do a little bit of mixers. Even if an oscillator is a very important component of a mixer, we're just going to see what mixers do. Rather, we'll look a little bit at the math behind the mixing. And then also, I would like towards the end of the class, while we review material, because I would like to bring everything together towards the end, we will also talk a little bit about modulation techniques, even if we're not going to look at modulation very extensively. But I would like you, since I spoke with a few of you about what are channels in the bandwidth and why do we have multiple channels and how do we modulate some signals. Of course, modulation is extremely important in a receiver. So that's what we're going to do afterwards. And then hopefully we'll be coming close to the end of the class. So I'm not going to do anything more for this class. I think we already have a lot of material and I feel comfortable finishing with some topics on modulation after we describe the topics like on next week for practice on amplifiers and then 1 week on mixers. Any questions you may have on that?
I have a question about last lecture's notes.
Last week's, yeah. Okay. And could you tell me that was specifically on the stability?
The amplifier stability circles that we talked about Wednesday, the gamma L and gamma S plane.
Yes, there.
So specifically, I'm a little confused as to the naming. So the gamma L plane is input stability and gamma S plane is output stability, which seems a little counterintuitive. So could you give some explanation for the naming there?
Yes. So if you, for me to show you that, I would like to go for a moment and find the lecture, which I believe was here because I was looking at that. That's why next week is needed. So look at this, all right? These are general equations. We found them using flow graphs. You find exactly the same equations using other, the traditional method from scattering parameters, do them analytically and so forth. Now, what do you find here, which is kind of interesting, that the input, I don't have right here. Let me see, I maybe have it on top. Let me see. I don't have right here the matching networks. We only have that. We had that in that lecture. But if I go back to what I was pointing to, let me see, there. Okay, you remember gamma in is the reflection coefficient as you look into your transistor, all right? Is like, so you have an amplifier design, and I will probably do it here, and then I will raise it. So in an amplifier design, you will have 3 pieces, 3 components, if you want to call them this way. This is your transistor with whatever bias networks. This is your input matching network. This is your output matching network. All right, do we agree with this?
Yeah.
Now, okay, what is gamma in? Gamma in is this one. All right, and what does it depend on? It depends on gamma L, which is in fact this one. All right, so practically, and then what do we do with gamma in? We make gamma in equal to gamma S for maximum gain. So practically the gamma L plane, the gamma L plane, which is the values of all of the gamma L's, impacts your gamma in, and therefore from gamma L plane you get values for gamma S. See, that's why there is this kind of confusion. And the same thing with gamma out. So if you keep this in mind, so gamma in depends on gamma L, gamma out, which is this one, let me do it using a different color, depends on gamma S, excuse me.
Gamma in depend on gamma L? Oh,
yes.
Yeah, it's correct.
Do you see that? Yeah.
Yeah, I see.
Okay, gamma S here. All right, now keep that in mind. All right, so and then we leave this and we go to stability here. All right, so gamma in depends on gamma L. All right, you see that here? And therefore, since gamma in has to be less than 1, but depends on gamma L, we call that gamma L plane, because the values of gamma L practically, they will tell you whether you are in stability, what values of gamma in will be less than 1. That's why they're so confusing. And then you go to gamma S, and since your gamma out depends on gamma S, that's why your gamma S plane specifies what regions of stability you have, which means that the magnitude of gamma out is going to be less than 1.
Okay, that makes sense now. Thank you for explaining that.
Absolutely. And in fact, you can even see it here. Look at this one. Here. Gamma in depends on gamma L in this equation. Gamma in depends on gamma L. So that's what you need to remember. And gamma S controls gamma out, or gamma out depends on gamma S from here. That's what happens in the amplifier design. So the selection of gamma S and gamma L is absolutely critical, all right? Because it's going to impact your gamma out, and obviously is not just gamma S by itself, but is multiplied with all of the scattering parameters. So what gamma S will make a given transistor stable depends on what values of gamma S, which are given by the gamma S on the gamma S plane by the gamma S circles, what values of those will make the magnitude of gamma out to be less than 1. Okay? That's why we have these names. And I decided to go on gamma L and gamma S because some of the books are using different ways of all the books that I look at call them gamma S or gamma L planes, but some books, they call them gamma out plane for this one. Some other books, they call it the input, whatever. I mean, it's kind of confusing. So I decided gamma L and gamma S will be more safe as opposed to getting confused. And also, it signifies that relationship. Any other questions? Okay. If we don't have any other questions, last time, if you remember, we talked about the following issue. Okay. Now, after the first thing we said, the first thing is stability. If your transistor has values that will never make either or both, in fact, gamma in and gamma out less than 1, then can never become an amplifier because it's going to always oscillate. Or in other words, if your gamma L circles and gamma S circles are outside of the Smith chart and they never intersect, then that for whatever values of gamma S and gamma L, then these transistors can never become amplifiers with the biasing that they have. So somebody will have to change the bias. We said that. The other thing that we said also is the following last time, which is also important for you to keep in mind as you think of that design. That when it comes to bandwidth and gain, if you go for maximum gain, you most probably, 99.9% of the time, unless it's a very special transistor I don't know of, but let's say 99.9% of the time, your amplifier is going to have a narrow bandwidth. All right? So you should always remember that. Maximum gain, most of the time, so you practically, for us engineers, meaning that we never look at 100% never means anything. Like 0% does not have any meaning because there is nothing absolute zero. And we are always in between. That means that every time if somebody tells you, you have to go and give maximum gain in your design, that you know that your bandwidth is going to be narrow. Now, how narrow, I don't know. Depends so much on the transistor you're using, the frequencies you are, how it has been biased, and the whole kind of thing. All right. And of course, it depends on your matching network. But the design is going to be narrow, no matter what. To be able to now improve your design for maximum gain, you can do some things, because in addition to having, just by the design constraints, a narrow design when you go for maximum gain, because usually and the reason is very simple, I mean, logistically, or like mentally, it's easy to understand it, because the maximum gain can be achieved. It's like one value you get. Is one value you get out of your amplifier, and that defines everything else. It defines your input network, it defines your output network. So it does not give you much flexibility, all right? It's one design at one frequency. Okay. And that means if it's maximum, if you go at the top value of the gain, everything that goes a little bit outside in terms of design, in terms of the frequency, you know, changes a little bit the center frequency, that your gain is going to go down, obviously. Now, we talked last time and we said, in general though, having that in mind, after you have selected the operating point, both in bias and in frequency, and your whatever other aspects of design in your amplifier, the next and the most important thing in controlling the bandwidth of your amplifier is your matching network. And last time we did an example where I tried to show you how, and then I had it here. No, I did not have it here. I had it in another one, on another, let me see. Was it in the, no, it was not in this one. Probably I had it in the stability circle. Yeah, yes, no. Do you remember when we did this example last time? In any case, I will find it. I will put all of this together because there are a lot of notes that I have. But last time we showed, or we talked about how when you change your matching network, how fast you change also the characteristics of your amplifier, not of your transistor. The characteristics of the transistor will change. Obviously, they're much more sensitive to bias than frequency, as you can imagine. But the matching network itself will definitely impact the bandwidth of your amplifier a lot more than the frequency change of your transistor characteristics. Now, what that means is that if you have a given transistor, and if you have then everything else set for you, whatever you want to, specific gain you want to achieve, specific noise you want to achieve, whatever, and then you decide what kind of gamma in and gamma out you're going to have in this particular case. And so let's say you're here, all right? This is a case of a unilateral transistor. Doesn't matter. Let's assume you got this one. And then everything else has been set for you. You set your expectations for design. And now you have already specified how much your gamma in and gamma S, gamma L and gamma S will be your gamma in and gamma out. Let's assume that you have designed that. You have decided on this, how much those will be, how much this will be. Obviously, for maximum gain, you see the complex conjugate match. Now, after that, what you have to do next is to have to go and design your matching networks. All right. Your matching networks have two things you need to keep in mind. You will have, depending, of course, on how they're going to operate, to introduce for lowest possible losses reactive elements, because if you introduce a resistor to match, you're going to lose a lot of power in the resistor. That's number one. Also, for high frequency circuits, most of the time, like more, I mean, the common thing for everybody to do, for every designer, is to use transmission lines. There are many, of course, for transmission lines, advantages of doing that, because introducing lumped elements may not necessarily be possible for the frequency, the substrate you're using, or the fabrication. Usually transmission lines have shown to become the better way of doing designs. However, you need to keep in mind one thing, that if you were to develop a design using LC circuits, like lumped elements, and then you translate the same design into a transmission line equivalent, your designs with the lumped elements will be more broadband than your designs with transmission lines. Because why? Why is that? Because we start with, in fact, in our designs, like you see in filters, with specifying the values of the reactive elements that we need to have for the matching. And then we realize the reactive elements with transmission lines. So like it is a stub sometimes, all right? an open stub, other times a short stub, or it could be a section of line plus a stub, and so forth, as you have seen in filters mostly, where it is, you see, in fact, what we go through to materialize it. But here is what happens. If you only have like lumped inductors and lumped capacitors, your frequency change comes through the omega, all right? So a reactive part coming from an inductor is a J omega L. And the reactive part coming from a capacitor, if in a impedance form, is 1 over J omega C. So they vary as omega or 1 over omega. However, if you try to change your L and represent your L with a section of line, in addition to omega and the change of the frequency you have there, you will also have a change in the length of the line in a way that is going to add additional changes in your circuit. And that's why you need to keep it in mind, always the lumped element designs are the best. Unfortunately, are very hard to do, all right? For 2 reasons. Because to pull, like if you try to go and get a transistor off the shelf, then you will have to place it. This is only possible for very low frequencies. For high frequencies, if you are to put lumped elements in there, let's assume you find them. I don't know how high you will find those components, but then you need to have holes to place them there. You need to find the ground. You need to solder it. I don't know. I mean, all of this becomes very messy and does not work well. And this, what is called the hybrid integration method. And then if you try to integrate lumps in like the form we saw, like an MIM or like a spiral inductor, then they have a lot of parasitic problems with parasitic elements, especially in high frequencies, and never work very well, all right? So there is always a trade-off whether you go for a transmission line or you go for lumped elements. Ideally, the lumped elements give you the best bandwidth, but transmission lines give you the least problems. So this is to keep in mind. Now, then what we said last time is we try to design an amplifier to have a gain of 10 dB at 6 gigahertz, and then we were given a transistor, and then we wanted to see how we were going to do this design. The transistor we were given practically was a unilateral transistor, had S12 equals 0, which makes calculations easier. So for example, from this mu that we have seen in the past, immediately, because of S12 equal to 0, this mu becomes larger than 1, and that makes the transistor unconditionally stable, and therefore you can do a good design. Okay, now they told us that they do not necessarily want to have maximum gain, but they want us obviously to get a different gain. And in fact, the reason for that most probably is because they wanted more bandwidth, all right, in this particular example. So then the question is, how do we then manage that? Okay, we know how to do maximum gain. How would we go about specifying now another method to go us into lower gain? Okay, now we introduced here 2 other parameters, this G sub S and G sub L. These are nothing else but ratios of the GS value over the maximum GS value that you could get, all right? And in fact, I would suggest that you also read the book, not just my notes. My notes are to help you, and then I can get rid of some extra stuff that is in the book, so to focus you on what is right. But you need to read the book as well. So here, for example, and let me see before, I don't know whether you remember what we had here for GS. Let me see here. The definitions for GS and GL are here. And they show you, as I said, the ratio of the value of GS versus GS max. And what is GS? If you remember, GS is the gain of this, and it's given here. All of these values are here. We have GS as the gain of MNS. And since you know, the gain is given by this, obviously we're trying to find gamma sub S. GL is given by this expression. And then we try to find gamma sub L. That will be GL will be the gain of this part. And then for G naught, we have the gain of that, of the transistor, and is S21. And then the product of the three gives us the transducer gain for this. And what we said is the transducer gain. Who will tell me what is the transducer gain? What is the definition for the transducer gain?
Is it available power divided by delivered power for a simple match?
Yeah, the inverse of that, but it's correct. And it's not necessarily simple match. It could be for that, but the most general definition of GT is like what goes to your, because we use it everywhere, right? Obviously in the simple match, that's what's happening, but the definition applies to many other cases. So GT is the value that goes to the load under any matching conditions divided by the maximum available by the source. All right, it's a very meaningful gain practically. So it's given by this. All right. Now we are coming back to our example. And we found these transistors are unconditionally stable from mu here. And then we found that G naught for this transistor is given by that from S to 1. But we don't know how much GL and GM are. All right, we don't know because we have not selected GS and GM, GS and GL yet, or gamma S and gamma L yet. So we don't know the values of GS and GL yet, but we know the maximum. And the maximum possible values would have been for what? When would I get these maximum possible values for GS max and GL max? What would those lead to if I get the maximum values? They would lead to maximum available gain for the whole thing. Do you agree?
Yeah, that makes sense.
Yeah, but we don't select those now because they told us not to worry about the maximum gain for the whole thing, but to look at getting something less, obviously, because, as we said before, somebody needed more bandwidth. Okay. Having said that, then we are looking, they told us to design it so GS is 1 dB, all right, and GL is 2 dBs, which makes GS, small gs, 0.79, large small gl, 0.765. And each one of those now values, GS and GL, are representing rather 2 circles. All right, what that tells you really is that GS and GL are not unique values for gamma L and gamma S. That's what it tells you. Even if GS and GL have a unique values, these are unique values, they can be provided by multiple values of gamma L and gamma S. Is that, do we understand this? So now, even if we found the values for GS and GL, we still have to find the appropriate gamma L and gamma S values. Okay, so now and that's where we stopped last time, I think, very briefly we went through that. Now we have two circles, and then you see the interesting thing you need to keep in mind is the circles have centers, and the center of the circle, of course, is a point on the Smith chart, which means that it has a magnitude and it has a face. And the face of this, which is here, so you see the magnitude 0.9 and you see the face. And the face of that is exactly the opposite of the face of S11 because of this. Do you agree? And the rest, of course, is just the magnitude of CS. And the CL too. CL has, of course, a magnitude, and the face of CL is the opposite of the face of S22. However, each one of them has a different radius, okay? Radius for RS, radius for RL. All right. So now we have from all of these, so here on all of this yellow, there is all of these values on the yellow circle will give GS of that value. However, of course, number one, we don't go outside of the Smith circle for gamma S, because gamma S is going to be the input reflection coefficient to the input matching network, which is passive. So the magnitude of gamma S has always to be inside the Smith chart. The same thing applies with the magnitude of gamma L. So all of the yellow points that go from here, and I should not move it. I should not know better than that. Okay, so all of the points here, from there to there, are appropriate points for gamma S. And all of the points here along this circle are appropriate for gamma L. Okay, however, you see which ones I chose. Why is that? Why did I choose the points gamma L and gamma S that have the smallest magnitude? Why do you think I did that? And then I did not, why did I not select this one?
It just seems to be the easiest to implement. It just gives off something like that.
I'll tell you why. It's not necessarily the easiest. I think the other one, this one too, could be easier, right? However, what happens is the following. The further out I'm going from the center of the chart is here. All right? You see that? The further out I'm going from the center of the chart, what is happening? The longer the lines and the longer the stubs I have to incorporate. Remember that? What happens if I have long sections of lines and long stubs? They change even much faster versus frequency. So the further out I am from the center of the chart, the more vulnerable I am to frequency changes because of my matching networks. All right? Or in other words,
Dr. Kateki?
yes. Yes.
I'm sorry to interrupt you. So
No problem.
At what condition will what things be more vulnerable to the frequency change?
So the further out the lengths. So if, for example, I have, let me show you what I mean. Let's assume that I have two transmission lines. All right, I have one transmission line here, which is this small. And let's assume that I have a length here. I have a impedance. And I have a transmission line here that let's assume is Z1, not Z0, obviously. And then I have a much longer line and have the same Z naught. Z naught, if it's 50 ohms, is in the middle of the Smith chart. Now, if I were to observe my impedance here and here versus frequency, as I change the frequency from the same F minimum to F maximum for the two circuits, I use the same low frequency and the same high frequency. This Z in, this one, is gonna change much less than this one. This here, Z in versus frequency, because of course the length of the line is gonna change. All right, so I'll tell you, and I will explain to you why that is. So here is the issue. I'm trying to explain to you why these two lengths, each one of them, the small one, let's call this D, is gonna vary versus, it's gonna lead it to much bigger, smaller change for Z in than the large one, L, that is gonna lead into much more bigger change for Z in versus frequency. And why is that? Let's think about it. It's simple. If I have D, which is small, and L, which is large, usually I saw them in wavelengths, all right? Let's assume that I have the same frequency, F0. So then my electric D, electric length, is gonna be the physical length divided by L naught. And this one, the electric length, let me call those electric by that, is gonna be L divided by L naught. Let's assume that this is 0.3 and this is 1.3. I mean, I exaggerate a little bit. Now, okay, you see those? Now I change my frequency from F naught and I go to 2F naught. What is gonna happen to D prime? D prime is gonna go to what? If I increase frequency, what happens to the wavelength? When I increase,
sorry, so if frequency increases, the wavelength should decrease.
yes.
Under
the
the condition
wavelength,
that the speed doesn't change.
yes, exactly. Assuming the speed does not change. Now, if the speed of light in this medium. Okay, now if I take that and I increase F naught, then my L naught becomes smaller. So, and if this becomes twice, this is gonna become half, which means that my new electric length for this frequency, F1, is gonna become 0.6, okay? And my new electric length is gonna become how much here? 2.6. How much, look, the difference. And on the Smith chart, we're talking about in wavelengths. We're not talking about physical lengths. So a doubling in frequency just changes your D from 0.3 to 0.6. And where do we go from 0.3 to 0.6? If I were to measure C wavelength, say towards generator, for example, this is 0 here. 0.3 will be here. Or maybe I could make it 0.03, all right? Just so I don't get twice. Let's make that 0.03, just for this example. 0.03, this one. So then this one becomes 0.03, 0.06. And I make that 0.3 just from simplicity. Make that 0.3, and that becomes then 0.6 here. 0.6. All right. From 0.03 to 0.06. So it was here in the beginning. This is point, let me see. Down here. 0, This is 0.3 here somewhere. So it was here somewhere, the point, if I had just the length. And now from 0.3, I'm going to 0.6, which is here. So my length moved by this much. If I were a stub, look how much I would go from this point.
Dr. Katehi?
Yes.
That's 0.06.
0.6. Yes. Here. And then, while the other one from 0.3 that was here, 0.3, it's here, it would go to what? 0.6. And where is 0.6? 0.6 goes 0.3, goes all the way around to 0.5 here, plus another, and 0.6 would have been here. So now, for that, I would have this change in the stub length. Do you see that? Look at how small in this, how big in this. Just because the length, two sections of line, because one is a longer length, the other is a shorter length, and I change the frequency the same way in both of them. So, do you understand then why two lengths you try always to go through shorter lengths in terms of bandwidth? Is that clear the way I described it, or it was not?
Well, from 0.3 to 0.6 is the second stop, right?
Yes, yes, the long one.
The first start
So
is 0.1.
Longer lengths travel faster around the Smith chart. Longer physical lengths travel faster around the Smith chart when we change frequency. Shorter physical lengths travel less on the Smith chart when we change frequency. When do we have shorter lengths in our stubs and lines when we match? If we are closer to
the frequency is higher.
If we are closer to the center, if we are closer, the closer we are to the center of the Smith chart, the smaller the dimensions we will have to accommodate in our physical dimensions, in our transmission line. Now I'm talking about the design frequency, right? One frequency, right? It doesn't matter whether you are at 100 gigahertz or 1 gigahertz, is the relative, all right? Because I always try to have shorter lengths, because if I have a matching network, two matching networks that do the same job, one has shorter lengths, the other has longer lengths, my shorter length is going to have less frequency variation, and therefore is going to be going to have higher bandwidth than my longer length. Is that clear? Do you guys understand what I'm saying, or it's kind of confusing?
I understand.
Okay. Anybody else? All right. So
the shorter the length, the higher frequency modulation, right?
Yes. So the shorter the length, the more your bandwidth. That's what you mean. In other words, all right. When you have less variation over more frequencies, it means you are more stable in your bandwidth. So you have more bandwidth.
Okay.
All right. So that's why now from these two circles, I chose these 2 points. I chose this yellow point down here, and I put a red also over it, and this green point down there, because from all of the points on these 2 circles, these are the closest to the center.
I have just a very quick question.
Yes.
When we pick gamma L and gamma S, we pick them from the actual circumference of the circle or inside?
Yes, circumference.
Okay, so it has to be on the line. Thank you.
Because of the values of gamma S and gamma L are specific.
Okay, that's what I thought. I just wanted to be clear on that.
Absolutely, yes. Okay, so, oops. All right. Okay, now with that clear, then you select these 2, your gamma S and gamma L. And because you select your gamma S and gamma L, what happens? Then you are ready to design your 2 matching networks. Okay? Then you don't look at your gamma in and gamma out anymore to make your gamma L and gamma S. equal to the complex conjugate, you're just having your gamma S and gamma L anymore. Do you understand that? And then you design your input and output matching networks using your gamma S and your gamma L. And you're done. Any questions so far?
I guess I have a question.
Yes.
So if you're trying to design for maximum gain, kind of like we said on the homework, would you choose RS is equal to the conjugate of RN, and same thing with for the output impedance network?
What for maximum gain, you will choose this one to be equal to this, and this one to be equal to this for maximum gain. All right. However, for gain which is not maximum, your gamma L and gamma S are chosen from this Smith chart. And are these two.
Okay. Yeah, because I was looking into that for the homework, and it seems like if you use those conditions, then you don't really get like a circle, because RS and RL, the radius of the circle, is like essentially becomes 0, I think.
Yeah, so becomes point, all right? Yes. So,
okay.
Yes, so actually, when you were maximum gain, you don't come to do these circles. There are no circles anymore, practically. So you don't look at circles if you want to do maximum gain. You know what you're going to do. You know that your gamma L and gamma S will have to be the complex conjugate of gamma in and gamma out. And we have formulas for that. You remember those formulas we've used?
Yeah, I think you're even on the notes too, I think so.
Yes. But if we don't want to do the maximum, then we have to go through this. And then we have values. Yeah.
And is that also true when the amplifier or the transistor is conditionally stable, or do you have to?
Yes, if it's conditionally stable now, it depends on where your transistor is going to be. Usually, all of the transistors we will see will have S11 and S22 less than 1. And in that case, you are inside the Smith chart. All right. The times when you have a sliver out here, you remember we saw in stability, you have a sliver out here. This is becoming more difficult because obviously you're already far from the Smith chart, whatever you do. But that happens only if your S22 is larger than 1. Or your S11 larger than 1. And we're not going to see that. I mean, in those special occasions where that happens, then people have more difficult of a problem, rather. But not for our class. Yeah, not for us. So for all of the examples we have, we are going to be inside the Smith chart because of S11 and S22 are less than 1 in magnitude.
Okay, yeah, sounds good.
Okay, now, since we got time, I think I will please look at your, over the weekend, at your quiz, since we did not, we're not able to do it in class because it's already 2:20, 2:30. And then please have it done by Monday, all right, before class. I know you also have your homework and you have your, but try to find some time over the weekend to do that too.
Can I clarify that actually? Quiz 11 was one that was posted before this class started, right? Is that the one that you want us to do over the weekend?
Yes, that's the one that is already, I have assigned it, I believe, but do it over the weekend because I was supposed to give you, but it's better. That's okay. I don't care as long as I spend enough time to cover this material.
So Dr. Katehi, there's a quiz due by the next lecture, right?
Yeah, Monday.
I see. Thank you. See you.
Okay. Bye-bye. Take care.
You are muted, Professor.